All right, so good morning, good evening, and good afternoon, everyone from all over the time zones. First, we are going to do a quick check. So I will enable the chat window for all of you, and just wanted to check if the audio and video is clear. So if you are able to hear me correctly, just type yes in the chat box. Just type yes in the chat box if you are able to hear me correctly. Okay, good. And if the slides is clear, if this particular slide is clear, just type yes in the chat box. All right, great. So great. So this is good, and you won't believe that this workshop, this particular webinar was planned in few hours, and the reason is because we wanted to. There are two events actually. If you look into this particular moment, there are two events. The first event is the RISC-V workshop closure. So we're on the last day of the RISC-V workshop. We had an amazing workshop in the last 5 days, where we had participants from close to 8 countries, and they basically designed their own RISC-V CPU in the last 5 days. So we wanted to take some feedback from them as well, which we are going to do later. I just wanted to see is anyone from the RISC-V workshop has joined over here? Anybody, just type yes in the chat box if you are in the current RISC-V workshop. So Charan, yes. So Charan, I'll unmute you, and you just need to share your experience with the others so that we can do a closure call for the RISC-V workshop. Yeah, Charan, you might want to share your experience with all the participants over here about your RISC-V workshop experience.
Okay, so good morning, good evening, and good afternoon to everybody from all the different time zones. And I'm Charan, and I enrolled for the RISC-V workshop. I was a participant of this workshop, and this was the final day of the workshop. So over the past 5 days, I would say this has been one of the most engaging workshops that I've ever attended. So all the 5 days, it was well structured. Okay, prior to the workshop, I had no idea about RISC-V course. I just had a basic understanding of hardware description languages and digital design, but I never knew that we could actually design a CPU core which was open sourced, because I thought everything was possible with proprietary and commercial tools, but all the tools which I used for designing the RISC-V core were open source tools. And then the introduction to TL-Verilog was something which fascinated me a lot, because I was practiced coding with Verilog, and often many a times I found it difficult to get the logic right. It was very difficult, but the extension, the transaction level Verilog was very seamless. It was very easy to use, and I was able to get the designs some of the features, like you need not define a signal for including in your logic. So all these features were actually these things were actually very helpful for TL-Verilog, and I would like to thank the team for introducing me to TL-Verilog. And then coming to RISC-V, so yeah, I just thought it would be very difficult to to start coding RISC-V, because it's essentially a CPU, and it's very difficult. It has a lot of components, and I might be stuck at times. But it was seamless. The way the course was structured was excellent, and for me it was just like every session, every video was just a continuation to my code. So it was like I was just adding features. I was just adding extra features to my code, to my design, and then finally, at the end of the day, I just realized that I designed a RISC-V code. Starting from the program counter, and then suddenly I was introduced to the decoder, and then after that you had this register read and write, and then ALU came, and then now after writing the test bench, I thought, okay, wow, we designed a RISC-V code.
Nice. So that's an amazing description. I think you described the entire thing in a very nice way. So good to hear that you were able to finish the entire workshop. Let's invite some more people. We have Vaishnav and Amin. So let's see if we have Vaishnav over here. Yeah, Vaishnav, you might want to share your experience with everybody quickly. I have just tried to unmute you. Yes, Vaishnav. Vaishnav, we are not able to hear you. So we also have Amin Altajer. Amin, I think these kind of opportunities you mentioned was not present, and you were very fascinated by this one. So we would like to hear a bit about it.
Sure. First, thank you so much, Kunal. I have a lot of respect to you guys. I'm actually from Bahrain, where we don't have a semiconductor industry.
Oh, okay, okay.
I do a lot of work in machine learning, and so I had a huge interest in this, basically in CPUs and in cores. And I got my hands with Verilog, long time back, but I never seen the whole thing from A to Z on how to build cores. And I was looking into your videos on Udemy, and I said, you know what, I'm just gonna go for the full thing. This doesn't cut it for me.
Okay.
And I was really fascinated with this first one where we built this core. But I had a couple of questions for you as well, Kunal. I'm not sure if this is the right forum to answer or maybe somewhere else. I know that Steve has gone for TL-Verilog, even though Verilog and VHDL are basically I would say the industry standard as of today. So I tried to get more resources online for TL-Verilog, and I've seen that Steve has gone a long way explaining TL-Verilog and such, but how do you feel about the reception and how the industry is looking at TL-Verilog as of today? Is it worth it to go and really, concentrate on the language for now, or just go back to Verilog and master that as well? So both languages. So what's your take?
Steve is here. Okay.
Oh, hey,
yep,
Steve
I'm
is
here. Yeah,
Steve.
it sounds like it's a question for me. So yeah, it's a great question. I'd be happy to answer it. Kunal, are you able to share enable video sharing?
Yeah, I can. 1 second. Steve, you can share it.
Yeah, okay.
And you can start the video also if you want.
What do you mean start the video? Oh, yeah. So great question. So I guess my perspective on that, first of all, so I get asked this a lot, of course, and a lot of my energy these days is focused on getting traction with universities to teach with TL-Verilog. Obviously, as you've seen in this workshop, there's a lot of benefits to learning hardware design using TL-Verilog, using MakerChip. And not surprisingly, that's the biggest objection that I get, is that the professors feel like they need to teach their students what's, quote, industry standard. And I find it kind of, it's a struggle and sort of a frustration for me, because being in the industry, coming from the industry and having the experiences and the connections that I have, I know that the industry is finally recognizing that RTL is just not going to carry us forward. It's not a solution. So the industry is not viewing Verilog as the language of the future. They're not viewing Verilog as what you would want to learn if you're trying to position yourself for the future. It's a legacy language. And yes, it's still, 70% of the designs in the world are Verilog. You absolutely need to learn it. You need to be able to work with these designs that are already out there in the industry. But to really position yourself on the forefront and to be ready to be the one driving the industry in new directions versus the one just supporting the legacy in the industry, you want to be looking to the future. And I can't make any promises today of where this technology will land and what form it will take, but I can tell you without a doubt the big EDA vendors are interested in this approach to circuit design. And so if you really want to position yourself as an industry leader, I'm not saying don't learn Verilog, because as I said, you may very well have to work with Verilog. But as far as positioning yourself for growth and to be one of the leaders in the industry and not a follower, absolutely learn TL-Verilog. Learn, there are other competing languages out there. Obviously, TL-Verilog is the one that I believe in most strongly as a technical vision. But certainly look to the future. That's my advice.
And Steve, you wanted to share some screen or?
I will share some things, but not in response to that in particular. I guess I can share some of the resources since that's a question.
Yes, you can.
Thank you, Steve. Really appreciate that, and thank you, Kunal, again. Because I was just wondering about the tooling for it. Like, if you look into Verilog, there's a lot of stuff that you can use, going forward. But for Verilog, I'm trying my very best in order to get tools, for production going forward. But again, thank you so much for this. I really appreciate the efforts and the great content. So keep it coming, guys. Have a great one.
Yeah, thanks for the great comments, great feedback, and Sharon as well. Very, very well said. I'm glad to hear that you had a really good experience with the workshop. As far as your questions about, sort of how you use TL-Verilog going forward, and how do you use this when the industry is using Verilog? So I've made it as easy as possible. I should say we've made it as easy as possible to use TL-Verilog, right? There's really no hurdle to enabling transaction level Verilog for Verilog designs. If your designs are open source, right? If you want this commercially, we have to go through, get you a proper license and all that. But if you just want to use this for open source development, we make Sandpiper, which is the TL-Verilog compiler, accessible in the cloud as a microservice. So all you really need to do to use TL-Verilog, to enable TL-Verilog in your Verilog projects, is to run these two simple commands that run in a fraction of a second. So actually this is the installation, and then to enable TL-Verilog on your files, you just send them through this cloud service, Sandpiper SaaS, to process the TL-Verilog constructs into Verilog. So it's really that easy. I mean, any project that already exists, open source project that's using Verilog, can use TL-Verilog just as easily.
So
and as far as
as
far as Makerchip, you guys were using Makerchip as a web, in your web browser in this course. It's also available as at least it appears to be a desktop app. It's actually running in your browser. It's running in the cloud, but you can use it to edit local files. So Makerchip app, you can run on any local TL-Verilog file and edit that file in the Makerchip IDE. So that's also very accessible for local work as well. And some of the students will probably talk about that in their projects as well.
Thank you, Steve and Kunal. Really appreciate that.
Yeah, and just to add on, Steve is also heading a project where we have written the RISC-V CPU core in TLV, and the project demands that everything should be done in Verilog. So we have a way where we are taking the TLV and we are building an SoC around it. We are doing something mixed signal, and I think within 2 weeks we are going to release that using Sky 130 technology node. So yeah, there will be tape outs also. We are going to silicon proof as well TLV, and that's when all these questions will be automatically. I mean, a tape out will answer all the questions. And I'm very sure that the project is going very well. In fact, there is also a thing which Shivani did. She has a webinar, full-fledged webinar, where we have taken the RISC-V CPU core, which was designed in TLV. Shivani, you might want to paste the link over here. So she has taken the TL-Verilog.
Yeah, we'll have Shivani talk about that, Kunal.
Okay, then it's good. Fine.
Yeah, why don't we see if the workshop students, anybody else has anything to say, and if any of you want to share your work so that others on the call can see what you did in the workshop, I think that'd be great.
Yeah, how about Charan or anybody who wants to share their GitHub link, and then we can quickly start with the webinar. So anybody who wants to share their GitHub link.
I'll also say, not to hide the fact that TL-Verilog is new technology, it's bleeding edge. There are, certainly rough corners to sand down. And I think what's exciting about it is that there is this energy with TL-Verilog, with the open source community and with students, and students are playing a very active role, as you're going to see, kind of as an intro to this call, in evolving that ecosystem around TL-Verilog. And that's something that everybody on this call or anywhere in the world could participate in.
Okay, so all right. So I think should we start with the webinar, Steve?
Yeah. Does any of you want to share your work in?
I just asked someone. Madhuri pasted. She pasted the other OPAMP project that is going on separately. Anybody wants to share the RISC-V TLV GitHub repo from the workshop? Amin, Sharan, Vaishnav, anybody? It's okay if it is not to the extreme perfect, but if you can share something, that would be good.
Yeah, or if you guys are a little shy, I'll pull up the workshop reference example for folks.
Yeah.
All right, no worries, I'll do that.
Okay, so we have Charan's GitHub repo on the Slack on the.
Okay, so let me open up Charan's.
Yeah.
All right, so this is Charan's work, and Charan, do you have a solution here that runs in Makerchip? Oh, this is great. So this one probably. Okay, you're not to that point yet. So that's fine. So let me pull up the reference solution for the workshop. So this is the repository that we have for the workshop, and here, what we have for the workshop is reference solutions for the students to refer to. So you can't see the solution in this repository, but you can't see the code for the solution, but we can see how that code compiles. So we're looking at an earlier example here where the students do a calculator, and this one would be the CPU core. So this is the Makerchip platform for those who haven't seen it yet. So you can edit code, you have a log giving you errors and so on. We have a block diagram, which for this example, since this is pretty large, may or may not show up. And one of the newer features in Makerchip is this visualization. So the students, as they're developing their RISC-V cores, have this visualization that emerges as they're developing their core. And this shows what the CPU is doing. So I'm just stepping here, and you can see the instructions that the CPU is executing. You can step through cycle by cycle and see which instructions are being executed, how they're being interpreted by the decode logic, and what's happening in the register file. And I think what I'll also do before we have the students talk is introduce Warp5. So in the Myth workshop, the students are designing their own RISC-V core. There's also Warp5, which is a TL-Verilog RISC-V core. And Warp5 is built to be highly configurable. So this is actually the visualization for Warp5, so a little bit more sophisticated, but very similar. And you can build a simple one-cycle core or 7-stage pipeline core. And at warp5.org, you can just go in, click a few buttons. Let's say I want to support floating point. And even as Vineet is going to talk about, I want multiple cores. You can specify your pipeline very specifically, how many pipeline stages you want, branch predictor, etc., some hazard parameters. Configure a few options for how you want your compilation to look. And down here, immediately, you've got your source configuration. You've got your transaction level Verilog for this design based on this configuration. And you've got your Verilog RTL. And we can open any of those inside Makerchip and edit our CPU to our heart's content. So yeah, let me just open the simple one. So this is the Warp5 core opened in Makerchip. And actually, I've opened this one up mistakenly. I've opened the Verilog, which means the visualization is not going to work because that's linked to TL-Verilog. But you can see that you can edit the Verilog inside Makerchip just like you can the TL-Verilog, etc. All right, so Kunal, why don't we jump into the students' presentations?
Yes, yes. So yeah, so I'll just quickly share the screen.
Yeah, do we want to start maybe with, as you were saying, with Shivani's kind of follow on to the workshop?
Yeah,
maybe that's
so
a natural
just,
one to look at
just
next.
Doing that actually. So my idea was to start with Shivani, and then we start with all the four, and we can do it a bit differently where the mentors introduce their GSOC students. But
We can follow this order too. This is good.
I can follow this order. Okay. So first of all, for all the participants, the reason we were able to club 4 webinars into one is because these are all demos, and everybody is going to give a demo of their work that they did in the GSOC project. So let's invite one by one. Let's invite Ninad first. So Ninad, let me.
Yeah, and just a little intro on all of these courses. So I've had really good luck working with students in Google Summer of Code. So Google Summer of Code is a program where Google sponsors students to work on open source projects. And so I've, for the past, 3 years, been a mentor in Google Summer of Code. And this year we actually had more mentors. We had these 4 projects running in Google Summer of Code, working on TL-Verilog projects. Each of these had their own mentor. And so for the most part, these are the projects that we're going to talk about today. And if anybody is interested in Google Summer of Code, if you're a student, it's certainly something to look into for next summer.
Sure. So let's invite Ninad now. Ninad might want to share his screen.
Yeah, thank you so much, Kunal.
Ninad, your voice is less. You just need to.
Is my voice clear now?
Actually, it's still quiet.
It's still less.
How about now?
Yeah. This is still better.
Headphones is better.
Yeah.
All right. So is my screen? Can you see my screen?
Yeah, we're able to see your screen. And there is a big stick which is to your right side. Is that there's a stick to your right hand side? It's a light. Oh, okay. Yeah.
Sorry.
Okay.
Actually, I sit in like a dark room. So.
All right. Sure. Please continue.
All right. So hello everyone. I would like to introduce you to block-based circuit design. TL-Verilog, as all of you have worked for the past 5 days on creating your own RISC-V code, you have been using this language. This project basically aimed to make it simple, accessible to younger learners, the people who are just getting introduced to TL-Verilog as well. And it just gives you a more visual feel for the entire code language. And as you can see, we have created like a lot of these categories where you have these blocks which you can drag and drop into the workspace. And depending on the block which you're dragging, you can convert that into your TL-Verilog code. And depending on this, you can, of course, write your programs. Actually, I myself was also part of the RISC-V Myth workshop. And last time I had tried to create RISC-V Myth code on this solution, but I had failed because the project was not there yet. I will just show you a small running demo of it.
Ninad, I think you need to speak a bit louder. I think the audio is.
All right, sorry.
Yeah, okay.
Yep. So when I was a part of the workshop, I was not able to get this solution up and running in time, but sorry.
But you did get your calculator circuit running,
Yeah,
I believe.
the calculator circuit was working, thankfully. So yeah, the calculator circuit worked. I really wanted to show everyone the RISC-V CPU code though. So that is now done. So I am just going to open this in Manycore for you all and run it. So basically, as you can see that there are a lot of blocks over here, which we have joined in succession to create our codes. As you can see, when we are coding with Fpga, like stages and like different CPU pipelines and stuff, it becomes very easy when you try to visualize it like this. You can see the different stages and all of the code which is going into those stages. Just as Microprocessor has its own blocking system over here, as you can see the green, yellow, blue. You understand these different kind of zones inside of your code, and everything is drag and drop. Again, when you are dealing with variables, like all of the signals which you are creating, you don't have to write it out every time. Like you can just like select, when you go to this, you get all of the signals you have created and you just have to select from those. So it becomes quite easy. There are not mistakes while like writing signals. Again, sometimes in Verilog, TL-Verilog, any programming language, when you're writing out each signal name, sometimes you have like a small error in like a spelling or something, and that creates a huge error in the program. And one of the most important benefits I feel for this solution right now is that you basically get all of the different kind of blocks you can code with in TL-Verilog. on the solution. So you don't have to go through any of the big documentations to really get started with writing your own circuits, designing your own circuits. So all you have to do is you have to explore this entire interface and see what all blocks are available for you to write with, to basically design your circuits with. And of course, it is a work in progress. A lot more will be added onto it. Right now, as you can see, we have had enough blocks over here to code our own RISC-V CPU. Going on to make a chip, as you can see, the entire diagram has basically spawned up. All of you have seen this diagram before. I'm pretty sure everyone was happy when their fifth day basically showed them their CPU running. Go on your cycle 61, you can see in the 14 register, your 45, 1 plus the summation of 1, 2, 3, 4, 5, 6, 7, 8, 9. So of course, that is a fun experience. As you can see, there is a lot of options which are available over here as well. This is just like another small circuit which we have coded, a Fibonacci tutorial from MakerChip. So you can open it in MakerChip. So when you click this button, what it basically does is it, so what it does is that it opens your code in MakerChip, your TL-Verilog code, and it compiles it as well. So it becomes very easy to see if your circuits are working or not. And with that, basically, you're able to check if there are any syntax errors. And very soon, I'll be trying to get a close integration with MakerChip going as well. There are just some basic functions like just take it to your clipboard. You can recover from the code. You can upload your own circuits, as I uploaded my my CPU code, and then you can recover from code. You can also, there is also a JavaScript option available. There are a lot of blocks over here, and very soon these blocks, I'm trying to get the Viz Alpha working. So as you see on MakerChip, you have this visualizations. Right now you have this registers and your text just showing what is those registers, the data which is stored inside of it. So this is done with JavaScript, the visualizations. So I'm just trying to get that working as well. So that will be another addition to the block-based circuit design.
Yeah, and then can you show how that JavaScript works in the nav-TLV?
All right, so in the nav-TLV, if you go down over here, so you will see that there's this Viz Alpha methods, basically blocks. Over here, we are coding our visualization tab in JavaScript. So there is a render each function in which basically we are getting the small blocks for that JavaScript visualization. So you might not see it in your editor over here, but in the nav-TLV, if you go, you can just see all of it written in JavaScript. You can study it and you can understand how to write your own visualizations as well. There are a lot of different tutorials on MakerChip as well. I think there is the game of life, the rule of life, one of the tutorials, which has the Viz Alpha method running on it. So this is one more thing which is this is an upcoming feature in the block-based circuit design. Very soon, everyone will be able to use that. I'm continuing my work on this project. Even after GSOC is over, I'm trying to bring it up to a place where it makes circuit design easier than it is to code it with your keyboard. Basically, drag and drop coding for your circuits. I hope that this can grow to a place where it can be used to basically show interest and like bring a solution and tool to people who want to learn circuit design, but they are afraid of it because of its hard complexity. And they can just get started with designing their own circuits. Maybe, of course, we have a TL-Verilog. You can also run this on FPGAs when you convert it to Verilog on your Sandpiper. So that is my presentation for block-based circuit design. And
yeah, I'm really excited about this project. I mean, you can see how this was a summer project, right? And you can see how far along Ninad got this project. It's really exciting. And I'm particularly excited, as Ninad said, about reaching a young audience with this technology. You know, circuit design, as I guess it was Charan was saying earlier, it's very unapproachable with the tools that the industry is giving us. And with this, we're trying to make this much more approachable. You know, even middle school kids will be able to jump into this platform. And, you know, it's not there yet, as Ninad says, this is still ongoing research. But much more approachable for young kids to get young kids excited about circuit design.
So one question for Ninad. Ninad, are you trying to build another Whitehead Junior? I think most of the participants over here, if you're from India, you might be aware of Whitehead Junior. Just type yes if you're aware of Whitehead Junior.
I guess I'm not from India. What's Whitehead Junior?
So it's like a Scratch Junior. It's like the one which you have in US, it's Scratch Junior. In India, we have Whitehead Junior, where it's a block-based C coding. They teach C programming just the way they're doing it. So that's very popular company in India. I think Ninad is in that, and that's $1 billion company. So
yeah, nice.
So I think 5 years down the line, Ninad will be a billionaire, maybe with this approach. Yeah. All right, this is good. So
Ninad,
yeah.
Can you show everybody one more thing? So maybe with the simpler circuit, the Pythagoras theorem circuit, just if we want to extend this pipeline, right? Maybe move the stage 1 logic to stage 0, or well, actually do that first.
So can you want me to move the stage to stage 0?
Yeah, right. So there, and then Ninad just moved a whole bunch of logic from stage 1 to stage 0, change the circuit in ways that would be, I don't know, probably take 2 hours in Verilog. And then Ninad, what if we want to take that stage 0 logic and include it in stage 2? Yep. So I think there was a little bit of lag there on our screen share, but just simple drag and drop of the statements to different pipelines. And with this integrated into Makerchip, which is not a very tight integration yet, you can immediately see in the logic diagram the implication of moving your logic to different pipeline stages.
Good.
All right, awesome.
So Ninad and Steve will do a small 2-day kind of workshop with this project. I think there are many schools who would be looking forward to this one, especially. So we have a system in India where 11th, 12th we can drop the biology and take up computer science. Remember, Ninad, I think you must be knowing about technical subjects. So that's where we can include this entire project, and where the students can also do it. So I have some thing in my mind. Maybe we'll plan out together and take this thing over there.
Thank you so
Yeah,
much.
fantastic.
Okay.
Maybe
Okay.
Kunal, maybe I'll jump in here with a quick screen share myself before we go on to the next project.
Yeah, I think you can share screen. Can you, Anil, can you stop screen sharing? Oh, yeah. I think you can share screen.
Okay. Yeah. So another thing that we have going on with Redwood EDA, kind of following on this theme. So I thought I'd follow up with Ninad's presentation. We're working on a community platform for Makerchip. So right now, Makerchip is this online IDE, and we're wrapping around that a platform to support community development on Makerchip so that you can save your project. And this is very early. This is very much a work in progress, but just to give you a sense of things to come. So within the community platform, you can find other people's projects, open them up in the IDE, make edits, save. We have already have this integrated with Git so that you can work on a project inside Makerchip, save it to your Git repository, and share it with other people. So this is something coming, and we're really looking for this to develop that community to really encourage sharing and participation, et cetera, as well as kind of extending this approachability of the platform for younger audience. And since I'm in the US, Scratch, or the platform Kunal mentioned for for coding, I imagine it has something similar to this. And this development actually is leveraging the Scratch front end.
Nice. All right, great. So this is good presentation, Ninad, and we'll talk post this webinar. And there are a couple of ways we can just expand this and make sure that even the smaller kids are able to do circuit design in a very nice way. And hopefully, you will be a millionaire. All right.
Thanks a lot, Ninad.
Yeah. Okay. So next we have Bala Dinesh. He is going to talk about virtual. He's going to demo virtual FPGA lab. So this has been a very huge requirement during the lockdown, especially during the pandemic, where there were no access to boards and people wanted to still do circuit design and FPGA design. This project has been of great help. Let me. Yeah. I think Bala, you have unmuted. I have unmuted you. Bala, are you able to hear me? And you can also start your video. Bala, we are not able to hear you.
Okay, am I audible now?
Yeah, you're audible. There is a lot of background noise.
Okay. Is it better now?
It is better now. All right. So this is let's welcome Bala Dinesh to showcase the virtual FPGA lab. This was again done under the GSOC project. Yeah, Bala, you can share your screen.
Yeah, so hello everyone. Myself Bala Dinesh, third year electrical engineering student. I was this year's Google Summer of Code project. So let me briefly show my work here. Let me share. So my project is about virtual FPGA lab. So using our TLV's WISP feature, we are just using how to mimic the same FPGA functionality in the web browser itself. So as you can see, like this, this is the project repository. So it contains step-by-step explanation on how to code this report. Like what basically this does is, let me show a simple example. So here you can see this is the WISP part, as you know already. So here I included the FPGA image and the log. These are some basic peripherals you might know have known already. This LED pins, this is a switch, and these are push buttons. So this example is about the LED. So you can see here, this is like the first LED is glowing up. So I coded this such a way that the LED is increasing like a counter. So you can see here, like for every clock cycle, we are increasing the incrementing the value of LEDs. So you can see, so once I move the cycle, you can see that LED is increasing like a counter. So it's basically here in this case, since it has eight LEDs, it's basically an 8-bit counter. So for every cycle, you can see that the LED is just moving up.
So is everybody able to see the LED glowing? Just type yes if you're able to see the LEDs at the bottom screen. Yeah. Okay, good. Continue, Bala.
Okay, so as you can see, like this is the basic this is the basic thing of this project. So we are focusing on many peripherals like this. So this one such example, this LED, and similarly we have 7-segment displays, and then LED displays, LCD displays, and many others. I will show you one by one each. So I can go through this like abstract of this project, and like you can use this awesome feature of this, and I can even just mimic the same lab environment without actually having an actual FPGA. So that's something which is really cool. So currently we are demonstrating 5 different kinds of boards in this part. So you see here now this is a Z board. So you can see here like the comment section, the order numbering. So 1 indicates Z board, like that. If 3 means basis 3, you can see the line number 26. I defined M4 board as 1. So if we give it as 3, you will just see a basis 3 board here. So we support 5 different kinds of board here. So it's actually the same thing with the basis 3 board. So if you're familiar with any of the boards, you can just type whichever board you want based on this numbering, and you can work. Similarly, if you are familiar with let's say icebreaker board, I just type 4, and you can see here this is just an icebreaker board. So same thing will happen here also, and you can, like, currently we have 5 different parts of board. So we kept as 1, 2, 3, 4, 5. In future we plan to add more boards to support more boards. So you will be seeing very soon about in more number of boards here. Yeah, so how this coding is happening is because you can see here in line number 27, I instantiated a TLV macro called FPGA init. So this FPGA init macro actually comes from this include file. So when you go into this link, you can see that the macro definition of this FPGA init. So what basically it does is adds FPGA image to this. So let's say if I uncomment these two, you can't see this FPGA image here because the visualization comes from these 2 macros. So once you initialize this alone, only FPGA will be initiated. So now LEDs won't be initiated because I didn't call this macro. So whenever, so now if I call this LED macro as well, this LED will function. As you can see here, this is a LED glowing up. So it's just like a square rectangular box made here. So this is a simple example for LED. Similarly, there are some other examples I can demonstrate. This is a 7-segment display. As you can see here, it starts at 0. So for every cycle, I'm just incrementing. So 0, 1, 2, 3, 4, 5. You can see as you can like this is basically like a 7-segment display works on the principle of like it has 7 segments. You can see, so for LED 0 in line number 23, you can see that all the 7 bits except the first bit is 1. So 1 indicates it's 0, and like 1 indicates LED is not glowing and 0 indicates glowing. So you can see here, like except the middle one, all these are glowing. So this is just basically a BCD to 7-segment converter. This variable. So for every cycle, you can see here, like I'm just incrementing. And then for the code for this 7-segment, you just want to instantiate this SSEG. This is a function for this 7-segment display working, and you need to pass three signals. So these three signals are just like whenever if you are familiar with the FPGA programming, whenever you want to interface with this peripheral, you need to pass those in XDC files, constraints files. So these are basically the inputs for those. Digit is the since we have 4 digits, this is the signal for that, and this is 7 segments, and this is for decimal point. So yeah, you can understand from this. If yeah, so yeah, the rest all the things are same. Yeah, let's move on to the next example. So this is an LCD display. Like you can see here, this is an LCD display, and I'm coded in such a way that like you can see, like after 100 cycles, you can see that FPGAs are fun. So I just texted in the way as we code in an actual LCD interfacing in FPGA. You can see the code base of this. And for calling this FPGA LCD display, I just instantiated this macro FPGA LCD and passed those pin signals. So you can see here, like initially everything will be garbage values. For every cycle instruction, you can see here in the top function set. So there are some different protocols for how to start this LCD display. First, we need to set the LCD, and then you need to display the cursor off. Cursor off means it just starts at the beginning of the cursor. So like, there are some other protocols. Now it moves to clear display. So whatever garbage value present before, it's now made to 0. So nothing is present. So after this, data instruction starts. So F starts, P starts, like whatever value we give in the code base here, you can just see the output of it. The cool feature of this this part in the FPGA Maker virtual lab is like you can cycle through it. So in the actual FPGA, you can't, like, let's say you want to go back and see how in each cycle it's happening, how each cycle the value is getting changed. You can't see an actual FPGA board because it just runs as it is. So here you can just, it's like a debug tool as well. And yeah, that's one more cool thing to work with in virtual FPGA lab. Yeah, so this is about the LCD, and then let's move on to next example. Yeah, this is on another example. Like this is basically a Ldr sensor. So for Ldr lights, I'm just mimicking this as a bulb. So consider this as a bulb of intensity 80. So when this is now currently very closer to the board, so you can see the 7 segment. Currently, the last segment is 9. Last digit is 9. You can see here, and then now it's 7 seconds. So basically, this value is 79. So for now, assume this. Okay, to be better, I just show with an Arctic 7 board. So an Arctic 7 board, you can see here, this is the Ldr sensor. So this is currently intensity value is currently 80. So whenever if you cycle through, this Ldr goes away from the light sensors, and you can see the display values getting reduced. So initially it was 80. So now you can see this is 6. This is 1's place, and this is 10's place. So 76. From 80 it moves to 76 because we are increasing the distance. between LDR and bulb. So this is just a simple example or demonstration on how to interface with the light sensor, and similarly you can work with other sensors as well. So yeah, these are some of the examples. There are more examples. You can go through this repository. Under example section you can see there is RGB, LCD, LED. LCD, LED I just showed you now, and there is light sensor, that's basically LDR, and then push buttons, slide switches, VGA also you can see, and then sound segment I just showed now. So yeah, like if you want to understand better in this, I made also a blog post to that. Once you click on this link, you can see, you can refer to this blog. So how each example is explained, each example is coded, I just explained here. So for temperature sensor, how to code it, some simple instructions to that, you can go through this as well. And yeah, so like you can see here, like how to select the board, you can, and then LED, how to instantiate, and then anything else. Yeah, one more thing also I explained, like let's say you want to add your own custom board. This is just a code for it. So what you basically do, copy this in any of this matrix. Okay, so let's say I just paste this here. This is a FPGA unit. So like custom, consider have this name as new macro FPGA unit custom. So for here you need to paste this FPGA board image URL. So for this I'm taking this FPGA. So copy this link. I'm just copying this link and pasting this link. So for calling this macro, as you know, like you can see FPGA unit, the new macro is custom. For now we don't want these things. So like we want to instantiate only this macro that we did now. So once we run this, you can see this is Z board image. This exact image comes here. So by this way, you can add your own FPGA images and work with that. Let's say suppose this Z board doesn't have 7-segment display feature to it. So you can work with some other board, something like that. And here, and also like in Z board, you can see 15 LEDs only. And some other boards have 16 LEDs. And something like that. So you can work according to your needs. So that's one thing about it. And that how I code this in LEDs, you can go through this. How LED macro is defined and how it is coded, the logic behind it, you can see. And yeah, the last thing is steps to run in an actual FPGA. As you already know that this Microprocessor TL-Verilog is synthesizable, meaning you can run in an actual FPGA board. So for the in detailed instruction on how to run, you can go to this link, and you need to basically run install the sandpaper. So basically what sandpaper does is converts for TL-Verilog to system Verilog or a Verilog. It's basically a compiler which converts TL-Verilog to system Verilog or Verilog. So you need to install that, and you need to just clone this repository, and then you need to run the shell script that's present here, this run.sh. Once you you can see in this picture, once you run this shell script, you will see that welcome to FPGA lab, going to the required directory. Now it will ask which file you want to upload on Vivado. So let's say you want to work with LED, just type LED here, and then it will ask okay. So I will basically show from this. So this is a run script I made, and then it asked me welcome to FPGA lab. Like I already run the script since like for generating bitstream and FPGA will take some time. So I already run this. So you will be seeing this like this, welcome to FPGA lab, virtual FPGA lab. And until you ask which file you want to upload, I'm just putting TLV files only. You need to give TLV files. So LEDs I'm just giving, and then it will ask the board. Like currently for running this script, we support 3 kinds of board: basis 3, HRTX, Z board. If you have any different boards also, it will work. Just you want, like you can see here, board is not from the given options. That you just write the part number of your board. So that's only thing you need to do extra. So once you give this part number, it will ask you, it will run the sandpaper tooling and all, and it will ask input clock frequency you want to work. So let's say if you're working with basis 3 board, So basic 3 board has a master clock of 100 megahertz. So in nanoseconds, it will be actually 10. But I gave 20 because I'm working with another board which has 50 megahertz. So once you did this, if you install Fpga software, it automatically generates bit stream, like synthesis, implementation, place and route, everything will be done by this. Everything will be done by this shell script. Basically, the shell script redirects to another TCL script. So by that, it will run, and finally it will program, and you can see the output. I guess you can see my video, right?
No, we are not able to see the video. Oh, okay, yeah, we are able to see your camera.
Okay, you can see my LED, like it's like I just gave a LED counter, so it's like counting. You can see here, it's like it's a binary counter. So the example that I demonstrated is just I just made into a bitstream file, and I just programmed it. Yes, you can see.
So everybody is able to see the screen. Just type yes if you're able to see the spotlight on. Yeah. Okay.
Yeah, by this you can even code your own designs, run it through this sandpaper tool. Like you have this automated shell script, right? So simply run this shell script. You will get the automatic like bitstream file. It will automatically program, and you can see your output. So yeah, so for beginners who are very new to FPGA programming, and if you don't have that much cost to buy for an FPGA board, you can make use of this opportunity and learn for simple FPGA, like for FPGA development. You can make use of this very cool web interface. Yeah, so without having an actual board, you can just work.
Amazing. So that's an amazing piece of demonstration. And since you know, I know the whole story behind your passion to develop this one. This really came up with your project, and for all the participants, I understand you have a lot of questions about how do you basically use this and things like that. Bad news, we have less time to demonstrate right now. But good news, Bala is going to do a full-fledged workshop in VSD Open conference. VSD Open is one of the conference where we promote a lot of open source, activities, and that's happening in the month of October. So Bala is going to do a full-fledged the workshop on the same project that he has just shared. So stay tuned to the website and we are going to let you know details about the entire thing. So you will be able to do the entire demonstration whatever Bala did on a virtual FPGA. Okay, thanks, Bala. Great presentation.
Yeah, thanks
Steve,
thanks a lot for demonstrating, making me demonstrate this.
Yeah, and Steve, that was a great piece of vision for as a virtual FPGA. I mean, this is the need of the day, and you really fill that gap for all the students globally, I would say.
Yeah, really great job, Bala. Thanks for sharing with everybody.
All right, so next we have RISC-V TensorCore extension for deep learning. There are a lot of questions about DL in the chat box, so we should quickly introduce Nitin Mishra. Let me unmute Nitin over here. Yeah.
I think Nitin's not here, is he?
No, Nitin is not here.
Okay.
But Theodore is here.
Who is?
Theodore Omzet.
Oh, Theo, you're here?
Theodore, you might want to unmute. I'm just trying to unmute you. Okay. I'm not able to unmute him.
Oh, yeah, he's on the list.
Yeah, right, you might want to do it.
Sure. Yeah, let me say a few words about it.
Okay, yeah, you can share your screen.
Okay. Yeah, so I'll keep this one fairly brief. So what I have on the screen here is actually a LinkedIn post, and I'm gonna, did I already share this? I did not. So let me just share this in the chat. So this post was midway through the summer, summarizing the project. And this was just handy for me to pull up to share Nitin's work. So Nitin's working on a vector processor for as a TensorCore extension. So focused on deep learning applications as an extension of RISC-V. And Nitin's work is really focused on leveraging what TL-Verilog brings to the table in terms of flexibility to create a platform for this TensorCore architecture for exploration. So just like we do with the Warp5 core, where it's highly configurable, you know, this project extends ultimately aims to extend the Warp5 core with this vector coprocessor for academic exploration. And I think we'll keep this one pretty short. It's a very interesting research project, not as heavily focused on Makerchip in particular. And since Nitin's not here, I think we'll move on unless Theo is able to jump in and add to the picture.
So I'm just trying to unmute him, but I'm not able to unmute.
Yeah, okay. And I know we're kind of light on time here, so why don't we move on? Vineet's got a lot to talk about with this project. And,
okay, so
Shivani, yeah. maybe before we go to Vineet, this might be a good time for Shivani to jump in about the course that she has.
Yes, Shivani, I'm unmuting you. Yeah, Shivani, you might want to explain about, because there are a lot of questions about converting TLV to Verilog and use it on FPGA and other things. So I think you're the right person to talk about it. So yeah, over to you, Shivani.
Yeah.
You can share your screen.
Oh, let me stop.
Yes.
Yeah, 1 second. Sorry for the delay. 1 second.
No issues. So what Shivani is going to present is, it will answer all the questions that everybody had about Verilog versus TL-Verilog. So yeah.
Yeah. So I think Steve mentioned that we can convert the TL-Verilog to Verilog using Sandpiper. So I would like to just brief first about that. So in my repository, so introducing myself, I'm a student at IIIT Bangalore, and I did this workshop of creating the RISC-V in this myth workshop in the second iteration, and currently the 7th iteration is going on. So when I did my second iteration, I myself was curious like how this is going to match the industry standards and how we can use the industry tool flow and get it dumped on either on FPGA or either through the ASIC flow, like how Kunal mentioned, he's also focusing now on getting it silicon proven. So this question came to my mind in that second iteration itself. So I moved ahead after this workshop. I tried to put it on FPGA. And then, so using Sandpiper, as Steve already mentioned, that using Sandpiper, we can convert the code basically to either Verilog or system Verilog through whichever language we are comfortable. And then we can, so basically once we have the Verilog or RTL in our hand, everyone must actually knowing the whole flow. We can either go to Xilinx Vivado, that is the proprietary tool, or either we can now open sources also develop much. So we can go through Viosis and basically the whole open lens, so that we can do the ASIC as well as FPGA using the open source as well. So that is there, and I'll paste this link in the chat. This is the my repository, which this is just the FPGA implementation of the workshop. And I also had written a blog post on how, one second. I had also written a blog post, my experience of how TL-Verilog is used for FPGA. So I'll not go much into my blog post, but I'll just paste it in the chat box. So once you're done with this call, you can go through this blog post. And then talking about the webinar, which I think Kunal mentioned the link. So coming to the webinar, what we are trying to do in the webinar is, I'll just share a piece of that webinar image. So this is the main purpose of the webinar. We are trying to mix the RVMIT and the PLL. So this is the RVMIT core, and we have a PLL through which we are getting the clock for the RVMIT. So we are basically trying to combine getting the analog designers and the digital design in the same box. So that is the whole idea what me and Kunal were thinking. People usually think analog and digital are different. So we are trying to mix both of them in the same lane and showing people that both the people can merge and then they can do big things in future. Yeah. So we took the PLL and the RVMIT, and yeah, and then in the whole course, we are focusing on the whole Vivado toolchain flow where we are using the PLL IP from Vivado. And then we are basically combining the PLL and RVMIT, and then we are trying to prove, we are dumping. Basically, at the end, we are proving that the core is working correct, but the clock is coming through PLL. That was the overall idea. And mixing an analog and digital IP, that was also the main focus while designing this whole webinar. Yeah, that's all from my side. I think Kunal has pasted the link. Yeah.
Yes, so I'll just paste the link again if anybody missed it. So this has got the full-fledged tutorial about about what Shivani did using Vivado mixed signal. So this webinar was specially designed to to handshake between analog designer, physical designer, and the FPGA designer. So generally, when I was working in design companies, analog people were different, FPGA were different, and digital designer, physical designer were all different. This particular webinar, we tried to bring everyone on the same platform, and we are trying to create a relationship between all the designers and showing them that every field is as important as the other one, and we should start respecting everybody's field. There has been a very myth, I would say, in the design industry, in the design houses, that physical designers are at the superior level, or artificial designers are at the superior level, or analog are at the superior level. So this particular webinar actually brings everyone on the same thing, and just to this is just to an attempt from our side to make sure that every field is equally important and equally challenging. That's what this webinar was all about. Okay, all right. So next we have a very interesting one. Thanks Shivani for the presentation, and I've pasted the link. Let them go through the Udemy course, and they will learn a lot about it. All right. So next we have 1 second. So next we have RISC-V Manycore Accelerator on Cloud FPGAs by Vinit Jain, and he has been mentored by Shivam Poddar. So let me unmute Shivam and Vinit both. Shivam has been unmuted. Vinit Jain. Yeah. So Shivam, Vinit, are you unmuted?
Yeah, I think it works for me too. Yep.
All right, great. So yeah, you might want to go ahead and explain this entire thing.
Sure, I'll let Vinit present, I think.
Yes, okay.
Is my screen visible?
Yeah, it's coming up. Just a minute. It is not visible.
We thought it was coming up.
Actually, it's a bit laggy in here. Like I'm using, like I have VirtualBox and many things open at the same time, so it's a bit laggy.
Okay, it did come through.
It has come through now.
Just give it a few seconds to settle. Okay, maybe I should stop sharing the show again.
Maybe you can stop your video too.
Okay. Is it visible now?
Yes.
Okay. So Shum, yeah, you can go ahead.
It is visible. We are seeing that presentation, and there are 3 MKB videos.
So Shivam, you want to go ahead?
Your screen is freezed, I think.
Is it not visible? Just
not yet. Maybe somebody else can share this and you can speak. That way, is it possible?
Okay, so just so I'm just stop sharing the share again. I think it might be okay now.
Yeah, you guys able to see your screen.
Okay, so we are talking about like open source development. My project idea was work 5 Manycore on the cloud. So as title already is. So let's talk about a bit about open software. So like open software has been evolving very rapidly, and it is leading to very innovative designs, and it's very flexible and it's available to everyone. So it's like open source and anyone can contribute and anyone can build their own like distros and all that. So a few examples are like Linux kernels, Git, Android, VLC, and we all use them in our daily lives. So open source softwares has been evolving and substantially from the past and on a big pace. And certainly nowadays we also have seen the cloud CPUs, and the advantage of cloud CPUs are like they have low hardware, low front-end cost, and like actually there's no hardware cost regarding that because we can just launch any cloud instances like Microsoft Azure or AWS F1 instances, AWS instances. And it's very flexible and it has a very dynamic scaling feature. So if, for example, if I'm using something and after a few seconds I realize that this is not what I need, I can easily upscale without having purchasing new hardware and all that. So the hardware cost is very much reduced, so which is helping new startups in terms of web application and open source web developers. So it's basically helping them. And also it's dynamic scaling and have better utilization over the system. And the software ecosystem, which is already been put out by the open source community, for example, GitHub and Git, it's basically helping them to leverage the open source open system. So talking about open source silicon, so what is basically open source silicon? So it's just like analogous to open source software. It's basically an open source in the hardware perspective. So recently we already have heard about RISC-V open source ISA standards, which is basically now complete open source, and anyone can use it in our designs, and anyone can propose their own extensions towards it, and anyone can contribute towards their effort. So RISC-V is basically an open source ISA, and it's promoting like it gains a lot of development. It gains a lot of interest among community and makes like a whole revolution about open source hardware design. And also there's one Skyward 180 nanometer PTK, which like you probably heard about, and it completes the one last gap regarding the whole open tool ASIC flow. So in ASIC flow, we do have like languages, we do have tools, but the PTK was basically which contains all the DRCs and all the specifications and rules for implementing a particular design. So these two standards, and also tools like OpenLane, OpenRoad, like OpenLane contains all these OpenRoad uses Magic, which is complete RTL to GTS2 format. So there's not like no restriction. So any beginner can just code up their RTL, and using OpenLane, they can convert your whole RTL to a GTS2 flow. And there's like a lot of enthusiasm among community, and what most of the community is contributing over that. So why it is different? So, and what it's holding up from our software domain. So first is the reusable IP design. So generally when targeting any specific implementation or specific hardware, so we need to be very sure about our design performance, and to implement to have a great performance, we need to have like specific timing constraints. So every device would have its own timing constraints, and each IP would be utilized in a different way, and to perform different application, to perform different tasks. So like the usability of IP has been a challenge. Another one is the cost of the EDA tools. So as you probably know that big Xilinx tools and commercial tools have heavy license under their terms, and also the availability of hardware. Like ASIC design is out of context for open source enthusiasts, and FPGAs are too available for like in a relatively cheap cost, but still like most of the crowd is it's expensive to all of them. So how are we facing this challenge, and how the industry's motive, and how we are like looking into solve this problem? So for the IP design, the industry's motive is to push design towards the high level synthesis or HLS. So in HLS, you can just program you just generate your RTL logic by writing your code in more abstract way, that is in C or C++ or OpenCL languages. And the tools will take care of all the implementation details and all the specific parts required by the hardware. So just you just implement your logic and let the tools build the correct configuration towards what was your target hardware. Also, we have the tools like one of the biggest problem with the HLS is that you are losing, it's really good in terms of computation, but you are losing a lot of hardware. You are losing a lot of controllability of your hardware. So like, for example, designing a CPU core itself, there are like a lot of scenarios in which you want to have a bypass or feed forward logic kind of thing. And you're losing basically a lot of controllability, and that's where the languages like TL-Verilog and others come into the picture. So TL-Verilog already you have seen in the workshop the advantages. So the biggest advantage of the biggest feature of the TL-Verilog is the timing abstract nature and ability to have transactions as a base argument. So it's basically upscaling over the RTL methodology based upon transaction methodology. So now, instead of RTL methodology, you are designing over transactional methodology, but you are not giving too much away from your hand. Also, languages like Chisels, BlueSpec, and Scala-based Spiral HTL into the picture. For the EDA tools, we do have like open source EDA tools like Makerchip, as you can see, SymbiFlow, which is called the GCC of FPGAs, which basically it's alternative to what Vivado is, and the EDA Open Playground in which you can just verify and do testing. So now coming to the third part is the cloud, is the availability hardware. So the cloud FPGAs are the one which will solve the issue. So the cloud FPGAs are basically the hardware. What we can do is there's a hardware accelerated computative kernels we can use for the web application and cloud application. So basically there's a host application and there's an FPGA. So for the application in which the host CPU takes a lot of time, which is kind of parallel in nature, for example, matrix multiplication, which is very good task for an FPGA because it's highly parallelized. So we can give that task to the FPGA to perform that application, and basically there will be a load balancing. So the advantages of using cloud FPGAs are basically, again, regarding the hardware upfront cost. So now there is no need to basically test for the different platforms. As soon as you made your bit stream, you can distribute to different people, and they have to just download the same bit stream over the same platform interface. So you don't need to also have to deal with the platform's issues. Also, there are a lot of advantages over this, as you can see. So talking about the Verve 5, so Steve has shown you about the Verve 5. So Verve 5 is basically an open source CPU configurator, and it can be optimized and it can be configured and as many as specification you want. So it can be compiled for RISC-V ISAs or MIPS ISA, or stages, depths, and multi-core, or you want pipelines, what type of branch predictor you want. Also, just to show what the Bala has showed you about the visualization feature. So visualization feature is basically visual debug is kind of like abstracting your design into an higher level. So you can view your model into a higher level of context. So I just opened this design in the source file in the Makerchip, and you can see the visualization. And as I proceed through the instructions, you can see instructions being fetched from the memory, and data is being computed by ALU, and it's dumped into the register file. And basically for loads and stores, it will access the memory. So coming back to TL-Verilog, like as I said, that it provides a very timing abstract property, and as also Steve talked about the TL-Verilog, and it's basically very flexible, and it's very there are a lot of syntax, and it's more abstract level, and you can probably read about this to get a better knowledge, to get a better idea about this. Not coming out the visualization. So as we know that hardware designing is fun, but the verification is the most challenging, and it's the most like long part. It takes 70% of your time to verify your design. And like, so what the visualization do is, it's a bunch of JavaScript code, and it is just to show. So it's a bunch of JavaScript code under this Viz alpha block, under this Viz alpha block, which is basically initializing your nodes and animating it accordingly. So you have the feature like how you want your design to be, how you want your visualization to be. So like this is the example for single cycle core, and this is the example for multi-cycle core. So we can see like if two instructions are dumped into different instruction memory, how our program will interpret, how it will visualize. So coming about my project. So my project was to basically take this whole Manycore infrastructure over the cloud. So part of the project was to debug multi-core itself, Manycore implementation itself. So this is a ring insertion ring, which is the hardware, which is an interconnect kind of between cores. So this is the input port of the this is the input port of the ring. So basically, CPU will give data or will give data into the ring, and ring will just pass it over into the main circle, and this is the output port for the ring, and this is like input port for the CPU. So the CPU will be attached here. So CPU is ejecting packets into the ring, and CPU will take into the packets into the ring. And the instructions is basically the reads and writes to the different core are based upon CSR's instructions, which are custom CSR's instructions. So the part of the project was to debug the design. As you can see that it's gone a fairly complex level that, and to debug this, like formally the idea would be to just take down the waveform and see where the packets are going. And basically it will be a kind of complex, and it will be a long time taking to debug this design. So it's where the advantage of the visualization comes in. So this is the insertion link, which I just coded up in a very like, so this is the JavaScript code for it. So these are a bunch of M4 defining the dots. So I can just change location from here, and it will reflect in the design. And it's basically initializing, and it's basically going into the waveform and fetching certain checkpoints. And based on that checkpoints, I'm animating the visualization. So as you can see that I already have a few set of instructions. So basically all cores are dumping like core. This is core 0, core 1, and core 2. Core 1 and core 2 are dumping data into the ring targeted towards core 0. So as you can see on cycle number 21, the data, the header flit is coming from the cores, two different cores at the same time. And this is the data flit preceded by the tail flit. So as we can see that how our design is working at every cycle or more abstract level. This is way easier to go into the waveforms and like open everything and see how the design is proceeding. And like also the colors of the lines indicating whether the data is valid, or like, for example, this red is indicating the data is blocked, and the blue is saying that data is valid. And we can see our design in more abstract level. So as you can see that there's a small bug in here that packets are always following this non-deflected path or going into the FIFOs. What they should be doing is they should be going through the non-deflected path. Like they should be going straight until and unless there's some packets ejecting into the ring. So like it helps after visualization, I quickly figure out the issues and fix that, and we discussed about architectural changes to the visualization. So this is the visualization over more abstract level. So the main purpose of the visualization was basically to do hardware designing, and you can go more into the depth how you want your visualization to be. But so like this is the abstract view, more general view, and this was built under 30 minutes. So as you can see that as going into the forwards, I can see the packets going into the ring and distant towards the core. Also, it also helps because our FIFO, our insertioning also supports multiple channels. So by multiple channels, we can see that which core is coming from which channel and which core. So as you can see that all those logic in the orange is from the channel 0, and all the logic in the blue is coming from channel 1. So the instruction which I'm replaying is that the core 1 is ejecting packets through the channel 0 and core 1 is ejecting packets through the channel 1. And again, this is the Viz code for that. So this is a maker chip, which is basically for Manycore, and this is the insertion link integrated to it. So based upon the instruction, you can also see how the packets are communicating amongst the core. So now coming back to the first class. So first class is the answer towards cloud FPGAs and how we can use this. So basically, this is the first class framework. All the logic in the green is what you have to implement. All the logic in the gray has already been implemented in the platform. So basically, we are using web client, web application, and we are communicating with the host application. So this is the web server written in Python and the host application, and that host application is communicating with the FPGA kernel. So this is basically the F1 in the F1 instance, and it's basically accelerating the web application because now our host itself is a web application. So we can write some logic. We can write a custom kernel. Let's say this core itself, single cycle core itself. So I can write the custom kernel for that single cycle core and use the web application to inject in the instructions and let the FPGA do its job and let the kernel output its data. And over the web client, I can see the output of the result. So just to show, so I've already compiled that in my local environment. So as you can see, I've already compiled this one over the local environment, and this is the web client. So this is a very basic, simple web client, and this is a bunch of instructions. So these instructions first will go to the sandpiper. First will go to the sandpiper in the cloud. Steve also shown how to use that, and it will generate a bunch of machine code, or basically 32-bit encoding of all those instructions, all those RISC-V instructions, and it will give that into the kernel. So as I press start, run. So this is the assemble code given from the sandpiper towards to this client, and the client gives data to the kernel. So this is the data. So this is the memory, and the first one is basically seeing the chunk type we are reading, and second entry is basically the address, and third is the instruction itself. So as we can see that the memory is getting loaded up, and as soon as also we are reading the instruction, the kernel will also spits data back into the web client regarding which instruction it's currently reading. And after all that, the output of the data is shown. So this is basically count to 10 program, and it basically does that job. So if I change something, for example, let's take a very simple logic that is splitting a single number. So let's take an arbitrary number. So I can see that 13, which is this number in hexadecimal, which code is sending us back. So this is the local environment. So talking about the local environment, so first class application has the main advantage that you can develop your own kernel over the local application. So this is the overall diagram of the local development. So this is your virtual box or like Linux box web client, and you can access the custom kernel. So this custom kernel is compiled through the Verilator, and it's basically ease the development flow. So you don't have to wait. So if you just want to debug your kernel for functionality, you just don't have to go over the cloud and start a machine and do stop. So basically this previous diagram is showing over the actual FPGA instance. Although there's one more hardware emulation mode supported, in which the custom kernel and all the corresponding shell logic is getting compiled, but it's very slow, and like we have seen that it's 100 times slower than what we can do over the local development. So this is the whole idea how the first class can help us in our design. To show some demo. So actually, it was quite laggy to run over all the things at a time. So this is a small video showing how I'm compiling the Manycore kernel. So this is Manycore kernel, and I changed the number of cores from 2 to 5. So it's basically a hello world program. So each core will split out its index number, and at the end, all of them will be added and split back to the web client. So I'm just like, you just need to type this only these commands only, and it will I fast forwarded here, and it will just compile, and you just need to go towards your local development. And this is a simple hello world program. And you can see the 10 is coming out. So basically like 0 plus 1 plus 2 plus 3 plus 4 is 10. Also coming to the actual hardware, actual FPGA. So you can also develop your instance over actual FPGA. So this is the Mandelbrot set application. So I'm just connecting to the through the SSH protocol towards my virtual machine. And all these processes are given in the first class GitHub repo, so you can look at that, and I will paste the link in the chat. And I've already built it, so I'm just using the pre-built flag to load the bit stream directly. And I did a small mistake here, and this is the correct one. So as you can see, this is the Mandelbrot set. And I'm rendering through C++. As you can see, the application is quite choppy, and I'm just going through the FPGA, and you can see that it is fairly faster enough. Also coming to a small example, which everyone can do is vector addition. It's basically a simple program, which is it's giving two set of instructions to the kernel, and the kernel will add both of them, and it will spit out to the back to the web client. Yeah, so this is the simple vector addition, and it's spitting out back. So yeah, I think that's from my side, and yeah, thanks Sonal and Steve to provide me the opportunity.
Yeah, great. That was a great work that you have shown. I think many students over here will be curious to do it on their own. So we'll plan something. We'll plan something out. How do we make sure that this is reached to each and every student? So we'll plan out something in that direction. And I see there is a lot of curiosity to for other students to use your projects and other projects as well. So something myself and Steve, we will plan out and deliver it to the students in a form of webinar or workshop, so that they can do more of hands-on. So great presentation, Vinit, and great job, Steve, for all the four projects.
Just want to thank Vineet for putting the presentation together. I think I think after this, maybe Kunal is going to put a blog post together about how you put a 100-person webinar together in 24 hours. I really want to thank everybody for just kind of last minute preparing to share this with everybody.
Yes.
And Vineet, his project in particular, I think it's really exciting to Vineet's project really brings lots of different components together, right? The Warp5 core that we've been working on, the first class framework is the framework that Vineet was showing for deploying hardware to cloud FPGAs. And then expanding Warp5 to support Manycore. Showcasing the visualization with that framework, animated visualizations, how you use that for verification, debug. So all these pieces really come together into a project that's significant in that, this is capability that the world didn't have before, to be able to, I showed the warp5.org where you just configure, I want this core. So, pretty soon you'll be able to click a couple buttons, get the Manycore that you want, configure that Manycore for a particular application that's meaningful to you, optimize it, build it on the cloud FPGAs, deploy it to the cloud, and make it accessible to everyone. It's a really exciting and transformational step to get to the point where, it's point and click to develop a real robust hardware accelerator that is accessible in the cloud to accelerate a web application, right? I mean, web applications, traditionally the limiting factor is performance, and now we have a path to not just getting adequate performance comparable to desktop, but getting performance that far exceeds what you can get from a desktop application, and that's a really exciting place to get to.
Yeah, and I believe there are a lot of professors also who must have joined this particular webinar. So it's a key takeaway for them. How do you basically incorporate all these learnings in their existing curriculum? And that is going to make hardware design really exciting. So it's a request for all the professors.
Yeah, reach out to Kunal and I, and we'll work with you.
So any professors over here, just type yes. If you are a professor in some college, just type yes. In the chat box. Oh, okay. We do have a lot of professors. Nice.
Great.
So it's time to sync back with them and see how do we take it to their students.
Yeah, I think you can really see from what the students are saying, both the ones that are participating in the workshop and those that are working on projects. Although they were all former students of the workshop as well, I guess.
Yes.
But how valuable this is in an educational setting.
Sure. All right. So finally, the last thing that we always do in all the webinars, it's a photo shoot. So everybody, I would request everyone to turn on their cameras, and we'll do a quick photo session for. So we do this in every webinar, in every workshop, and the reason is we just collect memories. We are collecting a lot of memories, and I'm trying to prepare a large collage for my wall itself, and that will hang behind my back, and try to prepare that. And that will happen with a lot of photographs. So everybody, I would request everyone to turn on their cameras, and we'll do a quick photo shoot for everyone. So yeah, Vatsal, Tanushri, Shaktivel, Mohammed, Aman, Supriya, Philip, Syed, Kalsai, GS, Bharat, Prabhat, everyone, Narsimha, Mayank, Professor Sudhakar, everyone, just turn on your cameras. We'll do a quick photo shoot. Anaga is going to take a quick picture for everyone. Nishita, Theodore, Rajesh, Vatsal, Yashodan, Bhuvan. Everybody can just turn on your cameras. Dipti, Mohammed Khalik, Akos. All right. So do we have a full house still? Matthew, Rahman, Shaktivel, Bhuvan, Rajesh, Vatsal, can you quickly turn on your cameras? And let everybody know that all of you are live. All right, let's do this V in front of the camera, and Anaga is going to take a picture for everyone. V is for victory. 4 webinars in 24 hours. I mean, that's a record. Okay. Anaga, did you take pictures? Yes. All right. Great. Thanks for joining. And I'll share the recording with Steve. You can upload it on the Ldr website, and I'll also upload it on my website, and you can access the whole recording out there. Thanks everyone for joining. Thanks Steve, and thanks all the GSOC participants. Great job. It's time to take it to the next level within the student community.
All right. Bye everybody.
Okay. Thank you. Bye.